Good morning, everybody. Welcome to the weekend session. The first talk will be given by Huijben from the University of Twente, and he will talk about lithium batteries.
Thank you. Yeah, so what I would like to show you is that lithium-ion batteries, which you are using continuously throughout the day on your mobile phone and on your laptop and other electronics, that oxides are crucial for this. And what I would like to demonstrate to you is that a lot of the knowledge that we used over so many years for studying oxide, optimizing oxide, getting cool new phenomena is something that I think this field is patiently waiting for. So we've been looking into these lithium-ion oxides for the last couple of years, but I think there is enormous opportunities to explore. And hopefully I can convince you a little bit. So within my group, we study oxides. We do this by using pulsed laser deposition to make them. And part of the group is studying battery materials. So here you can see a couple of the faces. Working on all kinds of different lithium-containing oxides. And I will show you which parts of the battery they can be important for. What I will show you today are the work that these three people have done. They were part of a grant I got in the Netherlands, which is finishing this summer. The person in the middle got recently a postdoc position in Münster at the Battery Institute over there, and the other two are finishing soon. If you think about batteries, and you would look up online, you will find very quickly that it was Volta who discovered the battery, and you will see all these old paintings. So Volta, what he did in the 1800s, he made a stack of two metals, copper and zinc, and in between them he put a cloth with some liquid. It was soaked in a liquid. And because of these two metals, and then they built up the whole stack, as you can see it over here with the cloth in between, in the end he could create a system where a voltage was created, and from top to bottom he could connect it to something else, and you can see how it worked. But if you really look carefully, this was something which was known already a long time before. So look back in history, already a couple of thousand years before, people were doing these kind of things where they had discovered old clay pots in the I would say in the Middle Eastern region, in Iraq. So they call these Baghdad batteries. And you can see here these clay pots, and you can see here a cross section where also these metals are there. So based on the same principle, you have two metals, you have a liquid in between, specific liquid, and then you can create voltages. And you can use these for different purposes. Well, nowadays, I would say we're very dependent on batteries. And all of us are probably all complaining about batteries because they don't do what you want, and then when you're using them after a year or two, they certainly don't do what you want, because then you have to connect your laptop almost continuously on the power cable. So crucial for a lot of these electronics is the power or the energy density. So it's power density, it's energy density. The energy density is certainly important. So you see over here, as an example, electric vehicle, Tesla. It can drive around 400 kilometers, but it requires a battery pack which is about 500 kilograms. Put it in perspective, you could also do that, oh, this is the Dutch word, you can also do that with gasoline. So there you have only 30 kilograms. So you can see that the density is pretty low. But this is the density, you see watt hour per kilogram. Now you have different type of batteries. For instance, in your mobile phone, it's a much smaller battery, but it's also smaller volume, and their density is more crucial. So you can see this is going up, and you have situations where you want to go down to the most extreme situation, and that's when you think about medical implants. The human body, they also put batteries in there. For instance, with pacemakers, and then you want to really make it as small as possible. But on the other hand, safety is much more crucial there. So then there's more a balance about maybe I should focus a little bit more on safety than on the smallest battery possible. But you can really see that it depends on your application how crucial this energy density is. And that's why lithium-ion batteries are being used, because that's the type of battery where the energy densities are very high. Now, and these batteries are, I would say, pretty common. All of you. Not all of them are lithium-ion batteries, but this is what you will find. What you immediately see is that they look very similar. And there has been studies done by a colleague of mine in the Netherlands for a Dutch TV program, where they were checking batteries which were the cheapest ones available in some kind of a supermarket and some of the most expensive ones. And he had to be careful with the statements. The only thing he could say was, they do exactly the same. What he meant to say is, they come from the same factory and they have a different wrapper around it. which is true quite often. So that if you look into the type of batteries that you use, it's not always exactly the same, but quite often it just depends on the branding and the marketing, how much money they can ask for it. So not automatically the most expensive ones are the best ones. So, the other thing, you're all using lithium in these batteries. And lithium is something that it's important not only for your health that your mobile phone is working completely, but also for your human body. You have a lithium level within your body, and that should be constant. Hopefully it's constant for most of you. If it drops, you become depressive. If it increases, you become manic. So people who have this condition, they're manic depressive, and they have to go to the doctor. They get extra lithium so that it becomes much more stable, but it's never perfect. But you get an extra, let's say, boost from some lithium. People knew that. So probably you are aware of the drink 7-Up. And you can see here it's lithiated lemon soda. Was lithium in it, and people got a boost from it. Nowadays lithium is not in there. It's the same as Coca-Cola. Some stuff was taken out at some point. But this was certainly there. Does anybody know why it's called 7-Up? So the up is the boost that you got. But why the 7? Mass. Look at the periodic table. So that's what he said. So there you can see it was indeed, this is lithium. So it was 7, you got a boost from it, that's where the name 7-Up comes from. Until a few years ago I never knew this, so when the director of this battery institute in Germany told me, I was amazed that that ever happened, and they made even commercials where they said, okay, just give it to your kid. So if you think about batteries, these are the basics. So this is the battery developed by Sony, started in the 90s, and which had an enormous impact. So you can see on the right side, on the cathode side, the positive here, you can see there are lithium cobalt oxide. So that's where the oxide is already crucial. So you can see it's a layered system. You have cobalt oxygen planes, and you have lithium ions in between. And those ions can move in and out very easily. And that's the energy that you store. How many lithiums are there and how much are you taking out? Now, during charging, the lithium ions move from this cathode side through the middle part to the left. And on the left you also have a layered structure, so you can move a lot of lithium in and out, but that's graphite. Pretty simple, relatively cheap of course, but you can see here it's moving in, and then during the discharge it moves back. So this is where the lithium ions are really intercalating into these structures with these oxides and going from left to right. The ions are moving through the middle. Of course, the electrons have to move on the outside, which means that the liquid electrolyte in the middle, it is an ion conductor, but it's electrically insulated. So it has no specific requirements for this liquid. It's acidic liquid. And that also puts a lot of restrictions on your battery. So you need significant amount of packaging to make sure it never leaks. These days it's pretty much better, but in the past some of these batteries would leak it at some point. It's a big mess if that happened. But you need a significant packaging to make the battery work, which means that from your weight, a lot of the weight is not really being used, only to keep the liquid in. And that's a big waste. The other point which is important here to point out is the layered structure. If I take out all my lithium, the structure will fall apart. So in these batteries, and the ones that you're using in most of your electronics, you only use 50% of the lithium, 50% of the energy capacity, and it's being limited by the electronics there. If you do this, if you take out too much, then the material will fall apart and your battery will degrade. And in a way, I think a lot of people are aware that maybe I should not charge my battery up to a specific level, because then I pull out too many lithium ions. But you have electronics in your connected to the battery which prevents this by themselves. But it's something where you could think about if you could make a different structure, and I will show you examples, oxide materials, then you could pull out all the lithium and you could stimulate that, let's say, much higher capacity. This was the starting point, and still crucial today. And in the picture also important is the cobalt. Cobalt is up to now showing the best performance, and there are big issues where in the world is cobalt being mined. Not only how costly is this, but also how much child labor is connected to this. So there are big programs that say, okay, we should get rid of the cobalt, but at least we should dramatically reduce it. The other issue is more about the availability of lithium. There are studies where people say, okay, there's not sufficient amount of lithium in the world to go towards all these electronic vehicles and all these things. There are the same amount of studies who say, okay, there is sufficient, don't be bothered by this. On the other hand, also, the batteries we have nowadays, we should recycle them better, and then you keep it in the system. So it's really the cobalt which is much more of a problem. So if you look to the standard cylinder, the battery, as you can see over here, yeah, plus and minus, but these are two foils. We have a cathode foil, an anode foil, then there is a separator in between, which makes sure that they don't touch, they're not shorted, and then you roll it up into a cylinder, as you can see over here, and then they pour in the liquid in a very simple picture. So the liquid is done afterwards. So that's why it's based on a cylinder. Everything is here based on foils which they connect, and in a smart way they connect it to top and bottom. Yeah, so crucial elements are these cathode, anode, and the electrolytes. Now this is maybe a little bit small, but if you think about batteries and the application, there's not a single battery which fulfills all the requirements. Showing you a little bit in the beginning. So people sometimes ask about, okay, which is the best material, which oxide, or whatever. It really depends. Do you want maximum energy density, or you want your battery to charge very fast? Maximum power density. Do you want the longest lifetime, lowest cost, or lowest toxicity? What else? That when you keep the battery in stock, that it doesn't discharge by itself so much. So it depends also on these things, how important they are, which type of battery that you would choose. In general, and this is from a couple of years back, you could say that the orange part is the lithium-ion batteries, the biggest part of the market these days. There is some lead acid, very important for in a car still. You have some nickel-based. These are sodium-based, which is new to replace lithium, but not that easy. And you have so-called flow batteries, which is a totally different concept. Then you have two containers with liquids, where the liquids are moving close to each other, where the battery performance is happening, and it goes back and forth. So this is for large-scale energy storage. You can see lithium is still very dominant. And with the trends where developments are going, you have the lithium-based materials we have nowadays. There are always improvements going on to make it somewhat better, more stable. If you buy electric vehicle now, it has a better battery in it than last year. So small improvements are always happening. But they're also looking at much more advanced lithium-ion batteries. At the same time, and I will show you also, it's about replacing the liquid electrolyte with a solid state. And that's again where the oxides will come in, I'll show you. So you remove the liquid. But that makes also that you can remove all the packaging. But you have also two other classes, which I won't go into detail so much in this talk, but you have materials or batteries based on lithium sulfur, and one based on lithium air. Lithium sulfur is something which is being studied and which is already having quite good performance. I will show you for lithium air what is the theoretical prediction, but people not even close to make that happen, although it has a very promising energy capacities. This is all lithium ion based, and on the other hand you can see that you have other ions. People look into sodium, as sodium is available everywhere and is cheaper. The problem there is that it gives you the same amount of energy. Lithium is 1 plus, sodium is 1 plus. Sodium is bigger, so it's much more difficult to move it as an ion through a crystal structure. And they don't, because of that, they don't have ideal cathode, anode, and electrolyte materials yet. But people do research into that. The other thing is to look into ions where you go from 1 plus to 2 plus. So you double your capacity in theory. The problem is that the ionic connectivity is much worse because it can also have all these bonds within the crystal structure, which are much stronger. People are even studying aluminum-based batteries, but there you go to 3 plus, is even more complicated. So I think probably can tell you that for a long time everything will still be based certainly on the lithium. Yes?
Just a quick question concerning the market of rechargeable batteries. Is it comparable to the non-rechargeable one? I mean, it was 120 billion. Is it kind of the same, or is it more important?
I wouldn't know the exact numbers for this. But you can see that these markets are certainly shifting. You can see the market of rechargeables enormously increasing, and let's say the batteries which you cannot recharge, I think they're going out pretty quickly.
We are still higher with.
So the ones which are not rechargeable, then the costs are even more crucial, because these ones, the lifetime can be, it's the amount of cycles that you can charge and discharge. And for some of these batteries, people think about, okay, they should do this at least 300 times, so that if I do it once a day, I can run it for a year. But that's the minimum, I would say. But if you have, for instance, applications where you need to recharge every once a week, and you can do this 300 times, then your lifetime, of course, decreases much more as you have these number of cycles. So if you put everything together, this was a nice overview in a paper from Kato in 2016. Kato was working at the Toyota research department where they're studying batteries for a long time already. And you can see here the power density, how fast can you charge a battery or some other devices, and there the energy density. In there you can see all kind of lithium-ion technologies which we have nowadays. You can see the direction where you go here with the lithium sulfur, the lithium air. There's a higher energy density, but the power density is pretty low. And here you can see the supercapacitors. You can charge them very fast and discharge them, but the amount of energy in there is low, as they're here on the left side. The one which is, I would say, rather interesting is here on the top. So that's where you have the solid state batteries, where you replace this liquid, where you have not the maxima, but you have a nice combination between a very good power density and energy density. And the research is to see how can we push it into this direction, so that you can ideally improve both. Well, that's hopefully at least one of them. Yeah, but if you look in the news, these kind of things happen. I wouldn't say often, but they happen. So hopefully it never happened to one of you. A laptop exploded on your lap, or a cell phone did this. That's why you weren't allowed to have the Galaxy cell phone on an airplane a couple of years ago. In the Netherlands, we really like to bike. Electric bikes is dominating the whole city and towns, I would say. So before it was old people that could buy an electric bike and still bike around. Now even the youngest people are buying electric bikes so they can go to school without being any effort. And so when I go on bike to the university, I have to be careful because young and old are passing by me like crazy. But the problem is, that was in the news a few weeks ago, that in a bike shop, on the counter, a battery exploded. And there were people standing around and had to be rushed to the hospital because in these batteries, I tell you, there's a liquid, a acidic liquid in there, which exploded and they got into everybody's faces. And when I heard this on the news, I told my wife, I said, they probably dropped it on the ground before. Something should have happened, that there was something shorted or thermal deactivated, thermal runaway. The process will happen, and what happens then is that oxygen is released, gases are created, and pressure builds up, and at some point it explodes. And that's what you can see here as well. You have heat being created, and at some point gases are released, and at some point the battery will just explode. This is the battery of an electric vehicle, of a car, let's say a Tesla. It's the full bottom plate. I don't have an electric vehicle, but I'm always amazed that people who drive a vehicle like that, if they are aware of what an enormous amount of energy they're sitting on top. Because this is what does happen once in a while with these electric vehicles. A few weeks ago it happened with one which was still standing at a dealer shop in my city, and they were still trying to investigate what happened. But this car burned out, but also the big part of the rest of the dealership, with all the cars standing close to it. I know that in Switzerland, if an electric vehicle burns, they're not allowed to take it through one of the tunnels. Because if then an accident happened, the tunnel is so expensive. So there are companies who build containers where you move the electric vehicle in, shut it, and then there is a whole system in it that if a fire starts, they can extinguish it immediately. So there's big business about things like this happen. So safety is a problem there. And I will show you in a minute why. So what is happening there, which causes this, and how we can prevent it. This is an overview of, let's say, the most important components. You have the cathode side, the anode side. Here you can see the potential against lithium. So on the top, around 4 volts, that's where the cathode materials are. That's where you see a bunch of the oxides. So here, lithium cobalt oxide, maybe you can put in some other elements, lithium manganese oxide, lithium cobalt oxide, with also some nickel, all kind of variants. Vanadium oxide is over here, manganese oxide. So these are the cathodes. You want as high as possible as a potential against lithium. Here you see the anodes. You want as low as possible, so that when you create them, you have the maximum voltage between them. So what do we use? We use, for instance, graphite. It's cheap, and you can see it's pretty low, so you have a big voltage. If you look to the capacity that you can get per kilogram, you can see the anode is better per kilogram than the cathode materials. So most research in batteries is done on the cathodes to improve this. However, a lot of the research is also by changing the graphite for something else, which is, let's say, a better performance. And what you will see is a lot of the research is focusing here on lithium metal, pure lithium metal, where the capacity is about a factor of 10 higher. You have to put only a little bit in it to have the same amount of capacity as nowadays, so it's not about to put more in, but the smaller volumes. But it causes problems. Lithium metal, I will show you in a minute, is not stable, so that's what people are trying to improve. So what we decided a couple of years ago to start looking into these oxide materials. These are materials which are with crystal structures, which is very common to us. We said, okay, let's grow them by pulse laser deposition in our lab, and let's see what we can achieve. From these materials, I told you lithium cobalt oxide was the starting point in the 90s for Sony. And this was also not, wouldn't stay the same thing over the years. So you can see here lithium cobalt oxide with the energy density. Here you can see the cobalt oxide planes with the lithium in between. Now, let's say in the 2000s, they replaced partially the cobalt because it was too expensive. They partially replaced it with nickel and manganese, but it also increased the energy capacity a little bit. So that was an extra advantage. And then, let's say something like 10 years ago, they started to put at the positions of some of these nickel, manganese and cobalt some extra lithium. We call these lithium-rich materials, and this increased the energy density dramatically. Those are the materials that you use nowadays. And you can see in here, it's the nickel, manganese, cobalt. They call this the NMC. If you look for batteries, they really like these abbreviations, so you will find batteries are NMC batteries, I think that, and it's this material. What you don't see here, what is the ratio between the elements? Let's say the point when they developed this, it was just 1 to 1 to 1. But they would like to drop the cobalt, of course. You want to just increase the other ones. So that's what they did. So first here on the left, you can see the capacities are okay. The 3 elements, nickel, cobalt, and manganese, are 1 to 1 to 1. And what is interesting then, the capacity is okay. thermal stability is reasonably high. So you can see about 300 degrees, that's when something starts to get into trouble, to decompose. If you drop the cobalt, because that's interesting from a cost point of view, and you just go over there, you can see the capacity is increasing, the thermal stability is decreasing dramatically. So research is going on to say, okay, can we make this at least? So where the ratio, so they call this NMC 111, NMC 622, and nowadays it's 811. So this 8 nickel, 1 manganese, and 1 cobalt. But they're all struggling here with the stability. And that's a big part of the research in battery studies. And I must say that the way that normal batteries are being made, I normally tell my students like this. Just mixing stuff. There's not really control on what can happen. They make powders, and they look into the grain sizes, what is the effect of making something smaller, you have a lot of surface area against the volume. And then they put coatings around it. And that's where the oxides come in as well. So the normal coatings are just to passivate it, aluminum oxide or anatase, titanium oxide, but also lithium tantalate, lithium niobate, and a lot of these oxides. But this is a problem, and this is where I would say a big part of the battery community is looking into. Here in the middle you can see NMC, nickel, manganese, cobalt, and that's a type of battery which is being used by BMW, Volkswagen, and Nissan for their cars. So what's Tesla using? Tesla was using for a long time the NCA, nickel, cobalt with aluminum. They just chose aluminum instead of the manganese, but it's a relatively similar material with some small differences that they chose specifically for this. And then you have other materials where there is no cobalt in, this lithium manganese oxide, which is being used by, for instance, BMW and other cars, Chevrolet or Nissan. And these are some of the pictures which they were doing in the last couple of years. Of course, I don't have an idea of what they will be using in the coming years, but you can see there are differences between them depending on which part they found most important. So this is what I discussed. Lithium cobalt oxide, energy power is okay. There are some other issues. This is what Tesla was using. Lithium nickel, aluminum cobalt, lithium manganese, NMC. And this is the one which is also interesting, which is called LFP, lithium iron phosphate. There are a lot of pluses over here. So why are car companies not using this? It's because the voltage it can deliver is only 3 volts.
No, I don't say it's also too expensive.
No, the point is that it's not as expensive because there is no cobalt or something in it, but just the energy that it provides you is lower. The potential is only 3 volts. But the good thing is it has a lot of pluses. It's very stable, it's very safe. So these are the kind of batteries which is used in electric buses. In the Netherlands, they're replacing all the boats on the canals in Amsterdam with this battery. So for the bigger vehicles, the really heavy-duty electric vehicles. Now, what's the problem which is occurring in batteries? It's at the interfaces. So in oxides, we really like to engineer the interface to look for really new phenomena. This is a terminology which is coming back in batteries continuously. So if you have the graphite, for instance, on the left, you have the liquid on the right, at these interfaces all kind of reactions are happening while you're using your battery. If you make your stack of materials for the first time, when we do that in the lab, and we start to charge and discharge, so you move your lithium in here and back, that's when you form this layer in the beginning. In your first couple of cycles, this is formed. Then hopefully, you can see there are all kind of different components with some carbonates, with fluorides. Now, it's quite diverse and it's not very well controlled. But normally it will stay there and it will stay constant, so then you have a battery which you can use and just is fixed. But this happens in the first cycle. So all the batteries that you're using, which are most of them are being produced in China, they produce them, then they set them in enormous infrastructure, and they cycle all of them a couple of times. So this happens, becomes stable, and then they sell it. So if they're wasting an enormous amount of energy because you need to cycle every battery before you do that. So if you could prevent this, that would be interesting. But it also limits the lithium transport. So it becomes constant, so you can use it, but if you could get rid of this, everything would be better. So people look into what kind of coatings can they put on top of the graphite to prevent this from happening. This is the so-called solid electrolyte interface. SEI formation, that's the abbreviation they use. A similar thing is happening on the other side, the cathode side, where people do research. Now why is this important on anode? If your anode is not graphite, but it's purely lithium metal, and the lithium has to go in and out, it's not always happening like that. If lithium through this liquid has to go from top to bottom, it doesn't go in, it sticks to the surface, and it forms these dendrites in each cycling. At some point, you have a short and an explosion. And that's what's happening in some of the batteries, where at the interfaces, let's say the reactions are not perfect, the lithium is not intercalating, but it's stacking on the surface onto these structures. And this is happening because if you have a little bit of the lithium pointing out, the field lines are focusing to this point. So all the new lithium are really focusing to this point. That's why it's growing out. It's not going into the rest of the structure. People are looking into if you put a coating in between, which is thin, so the lithium is able to do, but you have an influence on field lines, if you can limit this. So this is very much happening if you deal with pure lithium metal as an anode. As long as people cannot get rid of this, then there's no point of going in this direction. This effect is much less in graphite. And if I replace my liquid with a solid state, would that prevent it? A little bit, but not completely. Because these things even grow through a ceramic material. They force themselves through it.
What did we just see? That was a computer simulation or what?
Sorry?
That was a simulation, right? It wasn't...
No, this wasn't a simulation.
Oh, it's a real video.
Yeah, so this is, so this is a video where they really had the liquid and the two sides, and then they cycle the battery very fast so you can see it growing. And there's a lot of research, there are lots of simulation and everything, but this is something I found on YouTube from colleagues somewhere else, and it really nicely shows what is a possibility there. But just to show you, so the moment that something is shorted, you have this problem. So you also can find a lot of movies on YouTube where people on purpose short something. And how do you do that? You hit a nail through a battery. Then you have all the thermal runaway, gas happening, and at some point you have the fire, and this is what is happening in the end. So you can see that, of course, this short is extreme, but if you create a short and you have current running there, you have heat being created, thermal runaway. Now, this is why you have those problems with those batteries. So you can go from these standard cylinder batteries to something which is called solid state. Replace the liquid, you have something which is layered, you don't need the packaging, and inherently it's much more stable. So if you take such a battery and you put a light against it, it's a flexible one, the packaging is not so problematic, and that doesn't have effect on the light work. And these kind of batteries is something which you cannot buy a lot, but this is something where companies are making and they're putting it into products right now, so you can expect it to be available in the near future. And this is how it's being built up. So this is where a normal battery is stacked about different foils, and here's the solid state version where you have these different layers of these components next to each other. Yes?
What is the potential of such a solid state battery?
The same. You can use exactly the same materials. You just replace the electrolyte. So the cathode and anode will determine the voltage, and they can be the same materials. The thing is that to make such a structure, you need a totally different synthesis procedure. Now it's becoming something which is layered. So maybe you can do thin film deposition, or people use, let's say, the layers can be thicker, so people use inkjet printing, all these kind of, as long as you make layers out of it. You want to ask a question?
How important is the interface when it comes to solid state battery? Because we're talking about something solid, so the exchange of ions has to happen between three different solid layers.
Yeah, that's a problem. So what people do in the things that they create right now is to use, let's say, powders where you have grains, and then you have a different part, and they, in a way, they put it on the surface and they put them with pressure, so that hopefully they're in good contact, so the ion will move from one side to the other. That's exactly the point that why we do this, also this research, to show that if you have control over the crystal orientation and the connection between them, you will dramatically enhance the performance of these devices.
So these are just in physical contact or actually bond together?
Yeah, so I don't know in detail in the end, but they are created, they are physically pushed in contact, brought to higher temperatures so that there would be bonds between them, but they are never perfect. There are certainly a lot of defects in there, a lot of grain boundaries, which will limit also the not only the ions which need to move, but the electrons as well. The point here is that you need a different technology to make these materials, so standard battery materials will not make this switch. The ones who are doing this right now. What you see over the last couple of years, that there are new companies, spin-off companies, or probably new companies who step into this field and are developing this. And for them it takes quite a while. Research is also being done by organizations like Toyota, but you really have to see with other collaborators how this is being produced. Yes?
Right. So the lifetime is the same as a regular one, right? The only one difference is the shape.
No, the lifetime can also be very different, because all kind of reactions which are happening at interfaces over here don't happen over there, so that can dramatically improve the lifetime. But it depends on which material combination that you're talking about. Yeah. So what you can do is, if the light is working, you can even cut a piece off. It doesn't matter. When the scissor cuts it, there is a short, the light goes off, and then it's on again. And if you take light with it. So, and they also, when you hit a nail through it, it's no problem. It's short. You create a short between them, but there is no thermal runaway, there are no gases being created. So these, let's say, type of batteries are inherently very stable. Now, this is what we have right now, lithium ion, and we're going towards advanced. In a couple of years, you will see that with these materials, lithium sulfur. But the one that I was pointing out, lithium air, is all the way over here. So that people predict will at least take 10 years, maybe, to develop. And this prediction is out there already for a long time. So I'm not sure if people will be able to do that. But just to flash you what is the idea that people have there, theoretical capacity is 10 times higher than what we have nowadays. And it's based on the effect where you are able to move lithium from one side to the other. But at the moment you do that, oxygen is released, or oxygen is coming back in. So it's a different form in doing this, and there is significant research in this direction, but it's it is at these moments it's not successful yet to do this. Well, these interfaces are crucial. So the aim is to use the control that we have to enhance the connectivities at these interfaces, ionic and electronic connectivities, and to control these interface formations. You don't want any dendrites. You want to control the flux of the lithium ion moving back and forth so that this can happen very fast. You want to have good strain accommodation. You can imagine if lithium goes in and out, the crystal structure will deform a little bit, so you want to take care of that. Because if this goes extreme, your material will always crack. And maybe at these interfaces, maybe you can do something which normally is not available if you do more bulk processing. And if we think about solid-state batteries, within each component you have a lot of range and grain boundaries, but the most important is if you go from cathode to electrolyte to anode, what can you do there at the interfaces to maybe align the crystal structures so the lithium ion can move. Let's say if you have a layered structure, it moves much better within the layer than across to the layer. So if you can control that, you can improve this. Now, there are all kinds of strategies in which people try to control this interface engineering. You go from particles to go to smaller length scales. So you have more surface area compared to the bulk, so you have much more connection there. Make composites of different materials, dope it with different elements to improve this. Change the surface morphology, coating of specific layers, very often oxides, to limit all kind of negative processes, so that won't happen. But also maybe add something to the liquids to stabilize this much more. So that's something which is happening and which they can put into, let's say, the current technologies. You don't have to wait for this solid state. So the materials that we are looking into, and which is, let's say, the standard materials in batteries, are these three. So the one in the middle is the lithium cobalt oxide that has this layered structure, 2D structure. But there are two of them which are closely connected. So on the left you can see a lithium iron phosphate. There are the 1D chains in it where the lithium is moving. This is this LFP, which is very stable, but it only gives you a 3-volt potential. And here on the right you have lithium manganese oxide, which is a spinel, and that has a 3D structure, so the lithium can move much more easily in all directions. So you can really think about 1D, 2D, and 3D, where you would expect, okay, that if you start playing with crystal orientation, you would expect the biggest effect in only a few of them. We'll show you some pictures about how you can test them in our lab. The kind of measurements that we do, if you do charging and discharging, is where you will see that during a charging, you will see that the voltage, you provide a current, you will see that the voltage will go up. And then within a specific capacity range, it will do this, and then it will reach a number of something like 4.5. You can see that around 4, there are 2 plateaus, and this holds for lithium manganese oxide, the spinel. The fact that there are 2 plateaus means that at 2 different voltages, lithium moves into your structure. In the charging, it moves out, and discharging moves in, but there are 2 different locations where lithium can sit. And first you fill up one, and then you do the next. And if you discharge it, you take it out from one location, the other location, and then you stop. So for lithium cobalt oxide, it's only one plateau, because the lithium is always in similar positions. So these are the 3 materials I was discussing. What is interesting, if you look to capacities and the voltage at which these things are happening, energy densities, that the top one is the one we're using now because it has maximum energy densities. If you replace it with some nickel and manganese, you can see it's relatively close. Theoretically, it's roughly the same that you could take out, but experimentally, people are much more successful to take more capacity out of it. Here you can see a lithium manganese oxide, that's the one I will show you. There is no cobalt in, but you can see it has a lower capacity. Lithium iron phosphate, it's even a little bit better, but the voltage is lower. Now lithium manganese oxide, the spinel, it has some problems. So people have been studying this for a long time, and if you make a battery out of it in more bulk processing, what happens if you make it in combination with such a liquid electrolyte and graphite anode, you cycle it a couple of times and the capacity drops dramatically in, let's say, 25 cycles. It's gone. So you will never use that in a real application. And there has been some studies where they say, okay, the problem is that the manganese will dissolve into the liquid electrolyte. And the manganese, during charging, discharging, it goes into different valence states, and at a specific moment, there is possible to dissolve. And the thing that was predicted is it really depends on your crystal facet. Which facet is in contact with your electrolyte, and that will stimulate this dissolution. But if they normally make materials, they make all these powders, all the facets are available, or all, but many are available. This is not very well controlled. So this was our starting point to say, okay, let's see if we can do that. If we make thin films where we control the specific orientation towards the liquid. So I've shown you 2 days ago that we do pulse laser deposition in our group, going from something which is small to wafers. We've used it for a long time to study all kinds of materials with interesting magnetic and electrical properties, and we still do this heavily. But we also started doing this for lithium-containing materials. And here you can see several of them on cathode, anode, or even electrolyte, composites between them, and in some collaboration we also study some amorphous materials. And I must say, for instance, lithium cobalt oxide, as it is such a standard material, there are papers about this already quite a while. And when we started doing this, we thought, okay, let's take this standard material, let's make this, and then from there, develop further on. But as I said 2 days ago, I think it took us about 2 years to reproduce what some other people have done before. And the problem is lithium. Lithium is volatile, very volatile, so it's really difficult to see, okay, what do I need to do to get the material in the end, what I want to get, from all the parameters that I have, my starting point, my target, to really optimize this. And now that we have done that, and we can use the knowledge also towards all these other materials, now we can really study them individually and also study them in combinations. And a lot of this research we do in collaboration with some of these partners. So with lithium manganese oxide, it's a spinel material. You take strontium titanate as a substrate, as we all do as a starting point, although I tell my students, if you don't need to, don't do that. Terrible substrate. But it's a spinel, so the spinel fits reasonably well on a perovskite. But what you see happening here, you take the 100 orientation and you grow a spinel. Spinel is about twice as big. The A and the B direction are nicely aligned with the A and B of the substrate. With the outer plane direction, the C is then pointing out. But you can see I'm forming pyramids. And these pyramids sometimes are truncated, but they really clearly form pyramids. And that's because the 111 crystal facet is the energetically most favorable one for spinels. So the moment I grow it on 110, you see I have these kind of rooftops. And if I take a 111 orientation, it's very flat. So if you put this in a schematic picture, this is just, you can easily come up with this to say, okay, this had to happen if 111 is the most stable one. And in this pyramid structure, you can see some of those pyramids are truncated, so you have a 100 top as well, which is sometimes happening. So if you check this in X-ray diffraction, you can see the peaks of the substrate with the squares, and you can see that the peak here next to it, that's where you have your spinel material. It always has the same orientation as the substrate. And it nicely forms this spinel face. Except for the one with the 100 orientation. There you see 2 extra peaks, which is a minor phase of manganese oxide. And we think that's from these truncated pyramids where you have a top surface, which is 100, where it can much easier release some lithium. So that's where you create some of these phases probably. So we're not 100% sure. You can only see these 3 samples, by the way, were grown in the same run. So it was not a run-to-run difference. We just put them next to each other in one run. You can do that. And here you can see the structure with the lithium positions, with the 3D directions of where lithium can move. And then you want to test them. Then you have a substrate. We have a thin film on top. We want to test them as a battery. So you think, okay, starting point, we should also take a liquid electrolyte, the standard one over here, and we put some lithium metal on the top. We connect top and bottom. And we start to do cyclic voltammetry, which means that you're moving or you're changing your voltage, and you see if you can get a current out of it. So I would say this didn't work. Something similar like ferroelectrics go banana. So it didn't work. And then it's like, okay, we didn't grow the material well, maybe the lithium level is not good enough, but there could be other issues. And there was something already explained in literature, that what you needed to do is to put here the thin film of strontium ruthenate in between. But the problem was the band alliance between the spinel material and the conducting STO substrate, which was niobium dope. We were not able to get the electrons out. And people showed that if you put strontium ruthenate in between, that was better. So in the first starting point, we said, okay, let's do that. And then you have this picture, where you can see at specific voltages, you can see a peak. So if you go here from a low voltage to a higher voltage, this is during charging. This is the first peak. That's where the first position of lithium is taken out. This is the second, like this. So this is the second. And on the way back, you fill it back up. You go from this phase to this phase. No lithium, because you can take out 100% of lithium in this case. Now, these voltage differences is something that you can see, okay, that's what it should be. The difference between where those peaks are, let's say the voltage is over here or over there, this difference tells you about the internal resistance of our structure. So let's say if the movement of the electrons and ions, if this is limited because of things that are happening at interfaces. Now here the difference is relatively small. This is what you would normally expect in these structures.
Why is the discharge cycle, the cycles a little more decreasing than the charging in the lower one?
A lot more decreasing. You mean the peak here?
The left one, the peak, the benefit is what bigger.
This one.
Yeah.
Then what is being done over there? You mean?
Yeah, why is the peak so much decreasing in size?
Yeah. So what you see here is that which voltages, if you scan through this, are reactions happening. So, and this is different than when you have a structure where no lithium is in and is moving to specific spots, or when you have it fully, you take them out, because the connectivity of this material is different than when it's fully lithiated or not. So this is not automatically the same. But what I'll show you later, or even here, is that instead of only doing this cyclic voltammetry, you can also look at when you provide a current, what the voltages are doing, so what kind of capacities are you able to get out, and then you can see, are you able to get out the same capacity as what you put in originally?
So what's the volume change with the full delithiation? And I'm kind of surprised that if it's confined on a substrate, that you can fully delithiate.
Yeah, so the point is that the A and B directions of the material are aligned with the A and B directions of the substrate, but they're not epitaxially strained.
But it's still clamped on there.
Yeah.
Right? So there has to be some elastic part. I
Yeah.
guess to keep it fully.
Yeah, I don't know the number from top of my head, but I'll show you later on. We can go more extreme,
Yeah.
and we can deal with strain better than what's normally done in bulk. So what you can see here is that here things are being charged with different rates, so different currents. This is slow, so you get more capacity in than when you do it faster, then it drops, and this is during the discharge. And for the 3 orientation, so let's say from this picture you see that everything is working pretty well. Now, if I talk about fast and slow, I'm not sure if you've seen it. Yeah, sure.
I have a question from the previous.
Sure.
Just curious. You have the piece which you said lithium is being taken out.
Mhm.
Is it possible to tune this? Like, for example, if we somehow manage to adjust the texture of this interface between substrate and the deposited, is it possible to move this to lower or higher voltage?
No, so the voltage at which this is happening is the voltage at where and this will, let's say the reaction will happen within the structure. The thing you can move is, let's say, where you have top and bottom, if they would do this. So if they will come further apart from each other, you have more internal resistance, which is a bad thing, so that's what you want to optimize. But you want to have them as close as possible. But you cannot move this at once. So of course, if you change something in the structure, you do with doping, you can do that a little bit. But you're in this range of 4 volts. So for instance, if we replace part of the manganese with nickel, we go from 4 more towards 5 volts. Which some people do, because you can put more energy in there. But there are other issues there.
So, sorry.
Yeah.
You fully deplete the lithium in this?
Yeah. Yeah.
So like when you XLD or XPS, you use nothing?
Yeah, I didn't put the pictures in, but yeah, we do. So we cycle the material, we're going with from 0 to 1, and you do an X-ray diffraction, and you see the different crystal structures. We also have an electrochemical cell where we can do it on the diffractometer. Point is, it's a little bit difficult. These cells are normally being designed for bulk materials, and with thin films, we have a substrate, so we have to come from the front. So this is what we're optimizing now, so that we can do these measurements while cycling. No, but it's fully delithiated in this state, and there it goes to one and the other. And the values that we're getting is what you would normally expect as well, how much capacity that you get out.
But that doesn't have an effect on the stability of the structure at some point, like if you deplete after too many cycles, you should...
So this crystal structure is not layered, so there's a structure where you can, without lithium it's still a stable structure, and you can do this, and let's say in a bunch of these materials where you do this intercalation, you can do this over and over, it's stable as long as there are no other reactions taking place. And yeah, what we'll show you in a minute is that you can cycle it very often, and it's still very stable. You have a question?
So, yeah, can you describe again why you put in the strontium
Yes.
layer and how that affects?
So, what you have is that you want to get the electrons out in the end. This is what should work as a battery. The thing that we're investigating now is we know that this one directly on the substrate, you have a problem in the band alignments. So you're not able to get the electrons out, and it was already published with strontium glutamate you could do that. Then at least you could have working as a battery, but we're checking now what is the difference. At the same time, we're also using other conducting oxides like lanthanum nickelate and some others to have the same effect to see how much that improves. But for this material we need to do it. There are other materials on the anode side which don't require this extra layer, because then there is no problem with band alignment. So if you, yes?
How thick is the lithium manganese? How thick?
How thick?
Yeah.
I will show you some thickness dependence, but we normally go from, let's say, tens of nanometers up to a couple of 100 nanometers. Yeah. So let's say normal batteries, they would like to go to micron or several micron. But for the kind of study that we want to do, we don't do that. It's also these type of batteries, if you use them, we call them also micro batteries. They don't need to be that thick. You want to use them in applications where the amount of energy doesn't have to be a lot, it has to be in small volume. So you want to use them in electronics and Internet of Things, so these things where it's not smart to go to big batteries in the way that we do that. If you want to use it in a car, you have to also use different synthesis procedure where you really have to go to lots of microns. If you talk about a battery, it's about how fast can you charge and discharge it, which is a big issue. And what people indicate is the C rate. And the C rate, it's relatively simple. It doesn't matter which battery you take. 1 C means that you can charge or discharge it within an hour. And then you have to adjust your current to make that possible. Our thin films are very thin, so to get a 1 C, we need microamps. Normal batteries, which are much thicker, people need to go to amps even to make that possible. So what you do then is you study, if you have 1 C, you do that in an hour. If you have 2 C, you do it twice as fast, 5 times as fast, so it takes less time. But for a lot of the battery studies, people go to 0.1 C, so C over 10. You do it very slow, but then these measurements, they take forever. Luckily, as we deal with thin films, we can already get all the lithium out if we use, let's say, values around this, around 1 or 2 C. And even higher, they can withstand it. So if we cycle these lithium manganese oxides for, let's say, over 100 times, and you vary the C rate, so the current at which you do that, you can see the capacity which you're pulling out is high if you do it slowly, and it's going down if you do it faster. This is a little bit slower again, and then faster is going down, and then you bring it back up. So from beginning to end, it decreased a little bit because you went a range where you did it reasonably fast. But what you can see here is that when you try to do it 10 times faster than normally, that when you have it 100 orientation, you still have a significant amount of capacity, where in the 2 other orientations, this is not there anymore. And to our opinion, this has to do, so the orientation is the internal structure of your film, because on the top, the crystal fast is always 1:1, there's no difference. But the orientation, although it's a 3D structure, there's still a preference for the 100 for lithium to move a little bit faster through the material than the other ones. And that's what you see coming back here, that when you push it to this higher range, that's when it's showing up, that it really is still able to move with a higher ionic connectivity. Now these things I'm showing you here, this was published at the end of last year, this paper, if you want to look it up. And then we started cycling, of course, for a very long time, so we cycled it up to 1,000 cycles. This is from the beginning. These are 4 similar samples, all grown at a 100. So with these pyramids, you can see they're pretty similar. So there is a break here, but you can see, of course, it drops over time, but the drop is not that much. I told you for a lot of battery systems we want to cycle them about 300 times and then we're pretty happy. So if you do that, I think the numbers are pretty reasonable. And this material normally is thought of that promising but so problematic we should not do that. And I think what we show is that if you control your synthesis in a way that you control the real interface towards the opposite material or the electrolyte, then reactions are not happening and you can still use these materials in an interesting way. Now this is then for these materials, if you cycle them, you can see the capacity goes down, discharge capacity over time, which is normal, that's what you see there, but you can see the plateaus are not changing. So always the same voltage that you're taking out. And you can also see that in the CV measurements, where the first cycle had a very strong peak, the other side of the peak dropped somewhat, but you can see it didn't move, so the internal resistance wasn't changed. So I'm not showing over here, but we also do a lot of electrochemical impedance spectroscopy, so that you can study your system and you can really extract all the different components which are contributing to the impedance, from the ionic conductivity, electroconductivity, all the different things, which is not simple. You can do the measurements, but then to make a model which explains this, we're pretty lucky that we have an expert in the group who is retired, but not really retired. Yes?
So there is a sort of an influence of the charging rate on your sort of lifetime, can I call it? Is there also a similar effect for discharge rate?
Yes, there is. So these are even the discharge rates we would show you, because in this case we did both of them in the same speed, to do both of them fast. So this is something that you have to study about what the difference is, but both of them will have an effect on your material. If you try to do it with too large current, you're not able to get all the lithium in, or later to get all the lithium out. So one thing I want to show you is that this is a picture I've shown you before. If I discharge it, I have two plateaus, and I can get this capacity out. That's what people know, and they normally think about this material, okay, it just doesn't work that well. Possibility, if I do this is where I go from 0 lithium to 1. Put it back in. But this material is interesting, because what I can do, I can go to 3 volts, and I put a second lithium in, and I double my capacity. This material will allow that. The problem is, it will deform so much, if you do charging, discharging, you get the untitled distortions, that you can only do this a couple of cycles and then it's gone. You cannot cycle this for long. People know that this is possible, but they will never do that because you will really damage it. But why would you do that? You go your lithium manganese oxide, you double your lithium, you can see the increase in the capacity, voltages are the same. So then you would be able to achieve capacities which are close to this lithium cobalt oxide. And you double the amount of lithium. Of course, we have these thin films, so at some point in time, a student, let's give it a try. Normally, we're studying these peaks around 4 volt, but then we went down to 3 volt and back up. And these are the 2 peaks connected to that. You can see the distance between them. So there is some internal resistance, but also this was not too much. But you can see strong peaks, so there's a lot of current there, there's a lot of capacity. So if I put this in the other picture, this is what we get. This is normally the capacity that we're taking out, and then we go to 3 volt, and you can see we at least have the same plateau there. So we're pulling out double the capacity. And the thing is that what we experimentally observe is even a lot more than theory. But you have to be careful with this. We're dealing with thin films. So in these materials you have lithium which is stored in the bulk, but you also have lithium which is attached to the surface. And when the bulk is thin, in thin films, the surface is significant. In a big battery, it doesn't matter that much. So what you see here is the capacity which we normally use at 4 volts, the new capacity, but you can also see there is a big slope in between, and this is what we're studying at the moment. So what is the capacity at the surface and how much, maybe this is constant, and it's always there. But the interesting thing is that this is something we can cycle now also 1,000 times, and it's not decreasing. So our thin films are dealing in a way with these expansions and these strain in the materials where normally in bulk that's not possible. So I think this is pretty cool. We haven't published about it, so you're one of the first I'm flashing to this. But this is something that we're studying right now. Okay, so I talked about this, but the cathode side. Then if you look to the anodes, you could think about going from graphite to lithium metal, but yeah, I would like to study oxides. So, oh wait, I have one part extra. I will come to that. I will come to some anode there. We also looked, I want to just show this quickly, we also looked into the nanomaterial lithium cobalt oxide. Lithium cobalt oxide is this layered structure, you can see here. And if you put it on the open doped STO, on the 101, the layering is like this, it's difficult for the lithium to get up. You put it on different orientations, you can see that you can align these planes where the lithium, in the simple understanding, would be able to move out much easier. And in here, we take a 100, it would be around a 104 orientation. So we do that, we grow these three films, you can see that they are nicely oriented with specific orientation, and this indeed is the 104 in this lithium cobalt oxide. And also there you can grow this nicely in oriented layers and study the performance there. And there we see that these two peaks are around 4 volt, and if you cycle them, this is also almost 900 times. You can see the capacity drops a little bit. This is where we did a different measurement, and then you go on. And this is an indication of the efficiency. How much charge you put in, how much charge can you take out. You want this to be 100%. You don't want to waste any energy here. Now, and what we're doing now is to go into these NMC, replace the cobalt, deal with these issues. Good job. I don't have time to go into that. So what I wanted to show is the anode material, which is interesting. So it's the lithium titanate. But you can see it positioned here. It's a 1.5 volt. So compared to these two, the voltage is way too high. So would not be a very good choice. However, this material allows lithium to move in and out extremely fast. So for some applications, that's very interesting to use. So we said, okay, let's see what we can do there. And there, lithium is in not in a layered structure, but it's also a spinel. It's an inverse spinel, and there you can go from a lithium 4 situation to a lithium 7, and you go back and forth between these two. The prediction was, from a colleague of mine at Delft University, that if you have, let's say, a specific orientation, a specific crystal facet, that at the surface you would also be able to attach a lot of lithium. Where you could go to, I said, you go between lithium 4 and lithium 7 in these two materials. Here they say in the 100 and the 101, at the surface it's lithium 7, and this is not possible. But if you do 111 facet, then you would be able to attach much more lithium there because of the arrangements of atoms there. So this was only prediction. So we said, okay, let's see if we can study that. Similar as before, we grow these films, 3 different orientations. You can see that they are following the orientation of the substrate, with only a few minor peaks of some minor phases which are indicating that there is no, or there's a deficiency in lithium. If you look how those phases are aligned on an STO substrate, the 100, you can see the 4 peaks, so it's nicely aligned with the substrate in plane orientations. 110, the 180 peaks, and there on the 111 you can see it's also, let's say, with the same peaks, but you can see there's a doubling of the peaks. There are 2 options in which those rectangles or those triangles are rotated. And this is also what you see back in the AFM pictures. Squares, lines, and triangles. If you zoom in, you can really understand them, similar as the other spinel I've shown you before, the lithium manganese oxide. Same thing, spinel likes to be 111 crystal facets, so in the end you will see a little bit of pyramids, smaller than what I showed you before, these rooftops, and something which is very flat. And then we started to measure them against a liquid electrolyte, and you can see that from the first charge you have a higher capacity, but that's when all these reactions are happening at the interface, so where I said, okay, against a liquid electrolyte, these solid electrolyte interfaces form all these strange phases, they become constant. That's where you go from here to a situation where it's very constant during your cycling. But all three of them work very well. The thing that we could do with thin films, which is normally not possible, is play with the thickness. And what you see here, I won't go into detail all the different measurements, but what you see here is the thickness. This is for the 100 orientation. And then you can see the numbers for charging and discharging, which is going up. But you can see there's a linear dependence, and that's happening in all of them. But there's always an offset over here. And that offset is the amount of capacity which is stored at the surface. Everything else is a bulk effect. More material, you store more lithium. That's an offset. And that's something which you can only do if you have this control. You can show, okay, how much is there? And is there a difference between them? What you can see is that it's not so much different between them. There's a slight difference, but that's also because of some of the differences in surface morphology. If we do with different speeds, different C rates, let me put in the final picture. If I only look at this plateau region at the 1.5 volt, you can see that all three give me the same capacity. So material works well, the same lithium going in and out. If I look to the full range between 1 and 2.5 volt, then it depends very much on these tails as well. And then you can see that the 100 orientation is higher than the other two. But that's the moment where you also are looking into the lithium stored at the surface. And the 100 had these pyramids formed, so there is a much higher surface area, and that explains this difference. So it's not so much the crystal structure itself, it's only how much surface do you have available for the material to attach. Now, when we took those numbers, different speeds, different C rates, and we do that for the different thicknesses I've shown you before, you put them in a diagram where you have the different thicknesses, you have the capacities, and with colors the different C rates. You can see that when you do something thin and slow, you have a very high capacity. But if you make it thicker and faster, you cannot extract all the lithium out of it very easily. So that's something we thought, okay, that's something we should be able to model to see if that fits. Because very often we get numbers which are not even close to the theoretical what you would get. Is this because of just the way that you make it? So we collaborated, colleagues from Delft, and they did phase field modeling to look into if lithium would move throughout a material, let's say only from the top, this rectangular orientation. So that was not sufficient to explain everything. But if you combine it with a spherical contribution, which means that you have grain boundaries where the lithium moves in fast and then it moves in sideways, then you can nicely fit this data, I would say, in a pretty reasonable way to say, okay, then you have all the sort of trends that we see there. So that was, I think, a nice confirmation. This was published a few months ago. So in the final part, I want to go back to say, okay, I've shown you the cathode, anode, but I'm basically talking about the solid state. What kind of materials are those? So there's a whole bunch of materials that people are studying. So these are in the liquids, so that's different. But here you can see sulfide-based materials. But here you can see some of the oxides. So I will show you later a little bit clearer. But you have here lithium lanthanum titanate, this is perovskite. Lithium lanthanum zirconate, that's a garnet, which works well. And for instance, you also have your lipon. So lipon is an amorphous material. People use that, but it doesn't have the best performance. What we like to do is to focus on these two, the garnets and the perovskite. Garnets have a crystal structure, which is about 12 angstrom. It's huge. So if you think about the textual relation, that's all very difficult. We do study this, but it's not that simple. What we have to be focusing on is the perovskites. It's a titanate. You can think about, okay, then you can find nice matches with the materials I've shown you before. If you put it in context, so these are the ionic conductivities. This is the temperature on top. This is 1/T. And you can see all of the different materials that I've shown you before. This is where normal liquid is. It's in the middle, and it can only be successful in a small temperature range. That's why if you have heat being created in the battery, you also have problems. And this is where the perovskite is. So maybe at room temperature it's a little bit worse in ionic conductivity, but you can also make it much thinner to compensate for that, but it's reasonable. So we started studying these materials individually, this lithium, lanthanum, titanate, where we're also now making full stacks of solid-state batteries, where we use the previous knowledge on the anode, the cathode, together with this electrolyte, and to see if we can have this stack working as a battery right now. I can tell you the ones up till now, they don't work, to be honest, otherwise I would show you the data. The point is that the ionic conductivity of this layer, and it doesn't move the ions as good as it should be, because there is a very subtle balance between, on the A side, the lithium, the amount of lithium there, the amount of lanthanum there, and vacancies, because they have to be there as well. Structurally, we can see, if we do it on the 1-1 orientation, then you have these smooth layers. Structurally, you can see your X-ray diffraction, you can see the peaks of the substrate, peaks of the 3 different layers, they're all oriented, so that's okay. Structurally, it's fine. It's just the details into the specific stoichiometry. If we do it on the 1-0-0 orientation with these pyramids, that's a different story. Then you can see some of the phases, but you can also see anatas, you can see rutile, all kind of other things are happening as well. So that's not so stable at all. So in this kind of stack, we're focusing on this bottom one. So, what I've shown you is that now we have lithium-ion materials for the batteries. We go into the more advanced lithium-ion materials, but for the future we will replace the electrolyte with solids, and a big direction is in replacing the anodes with some lithium metal. But significant research has to be done there, so that you increase the energy density going up the scale. At the same time, there is lots of research which is not based on lithium, which is much more on bigger volume, stationary storage, volume, costs are lower. So you will also see a lot of research which is on totally different subjects, where even aqueous electrolytes and things like that. So, no, not everything. So what we do is we try to use all our knowledge to control the orientations and the interfaces and optimize this and learn from it. No, you cannot see it, but to have optimal electrochemistry. But we also do study the interfaces in detail, the TEM, to see, okay, how the crystal structures align and what kind of maybe problematic interfaces are happening there, so that we can combine all this in real combination of such a thin film solid-state micro battery. Now, this is not work that we do on ourselves, so we work strongly in collaboration with partners also in Germany. So the University of Twente is at the eastern border in the Netherlands. Close to us we have the University of Münster with a very big battery institute. We have about 200 researchers only on this topic. We also collaborate with Forschungscenter Uni. It's also only a 2-hour drive, so I have a guest position there. We also strongly collaborate with companies. So these are 2 companies which are even in our region. So the top one, they're there and they're going to expand there. Lithium Works, it's also been located in the US and in China, and they really produce batteries, materials research and chemistry. And this SuperB is a company who does assembly of batteries. They get their basic batteries also from them, and then they assemble into real applications. So they are putting them, for instance, in these electric buses and electric boats in the canals of Amsterdam. At the same time, we're also looking into how to set up a much stronger collaboration within our country. Battery research was not being seen as being important by politicians. It's a Dutch problem. Politicians have no background in science, so they don't care so much about a couple of topics, so we really have to convince them. But we're setting up a big collaboration with a lot of universities, companies, to see that we can stimulate this. And at the same time also being part of a bigger European network. So Alistor is one of them, where a lot of labs in Europe are collaborating. The picture is not correct anymore because there are also some German partners these days. And I'm not sure if you're aware of this, Europe is also working on a new flagship. The flagship is where they put a lot of effort into new programs. They're working on a new battery flagship, so hopefully that will start next year. Where you can see at this point there are a lot of these partners who started it. We're not involved in this process. And you can see an enormous amount of companies. We're in that now, we're expanding. So I think that's very good. And lots of opportunities for real detailed science into these materials to get much more understanding. And I think that's also, we're not working on this topic for many, many years, but very quickly we became part of all these networks, but it's something which is totally different than everybody else is doing in this field. So please join and see what we can do. With that, thank you for your attention.